In ancient times, labour was cheap and unhurried. The king didn't mind if it took thousands of slaves a lifetime to complete a structure. Huge monuments were built of solid rock. As engineering techniques improved, hollow structures could be built that used less materials and labour. Nowadays, we've learnt about the forces within structures and can build with the minimum amount of material. A structure has a variety of forces within it. This coal loader has some parts being stretched. We say they are in tension. Other parts are being pushed. They are in compression. A sideways force is a shear force, and a twisting force is torsion. The challenge is to build lightweight structures. With practice, you will be able to work out what the forces are in a structure and then use only the minimum of materials. If something is hanging or pulling, we call the force tension. This is the world's biggest mobile crane at work building a stadium. The force in the rope is always tension, as a rope cannot push or twist or shear. The forces can be added together by adding more ropes to share the load. The crane is supplying a matching pushing or compression force which always balances the tension force.
A web, on the other hand, is a little more complex. It is a tension structure with every part of the web in tension. A tension structure is very light, easy to build, and often has beautiful curves. It's an easy way to produce a saddle shape or a whole variety of related shapes that would be difficult to build in any other way. Sails are tension structures, as are tents. It's not possible for a tension structure to exist by itself. It needs to have a framework for the ropes to pull from. In this case, the poles are in compression and must balance the tension force. The beauty of a necklace is the shape it hangs in. We call the shape of a hanging chain a catenary. It doesn't matter how hard a chain or rope is pulled, it will always sag a little, producing a family of catenary curves. The chain sags because it has mass evenly distributed along the length. We can see this curve on power lines or the cables holding up a suspension bridge. The roadway is suspended from the main cables by stringers, which are in tension. The cables on the Tower Bridge in London trace out part of a catenary curve. Suspension bridges give the maximum span for the least materials. Most of the traditional bridges in Papua New Guinea are suspension bridges made of vines. And when modern material, such as fencing wire, is used, a truly lightweight structure can be built. However, the supporting wires need to have as much sag as possible. Otherwise, the forces become too great. Here, the force produced by even one person was great enough to stretch the wire beyond its elastic limit, causing it to sag. The unnerving thing about suspension bridges is that they move. In Nepal, it is easier to teach the yaks to adapt than to build a stiffer bridge. A balloon is a tension structure. The skin is in tension and the gas in compression. Can you work out why high-pressure gas is stored in a sphere or in cylinders? And why are the ends domed?
The person on the bottom of the column has force pushing from above. He is in compression. If we hold something heavy above our head, we can feel it pushing us downwards. It compresses each part of our body. Too much will do damage. This ancient column has a break typical of a column that has been loaded until it broke in compression. Compression produces a 45-degree break. If we wanted to hold a load above a space, this is one way to do it. Shear legs, as these are called, are best with a single load. Each of the legs is in compression. If we had two forces, this shape gives us compression forces in all members. And again. And 7 forces. This drift of snow has become compressed to ice, and the river has cut a tunnel through it. The shape that has formed is an arch. Wherever the ice is in tension, it will hang, creep, and eventually break off. Finally, only the ice in compression remains. So here nature has, by balancing its forces, produced the perfect shape for a tunnel. When the miners drive a tunnel, or adit as it is called, they want to stop the roof naturally forming an arch. They must drive cables or long bolts into the roof to hold it up. It is called roof bolting. If they don't bolt the roof, rocks will fall on them until a natural arch is produced.
The arch was a brilliant discovery, which became widespread when the Romans adopted it in their buildings. These Roman ruins in Turkey are 2,000 years old. The arch can be made of blocks of stone with no cement. They lean against each other, holding each other in place. The larger the load, the tighter they are held in place. The important thing to remember is that every block is in compression. The London Underground Railway was bored through soft clay, which when wet pushes in from all sides. The tunnel is a complete circle, which is why the train line is called the Tube. The lightest dam is the arch dam. Every part of the arch is in compression. A dome is simply an arch rotated 180 degrees. The principle is the same. Most arch bridges have the road on top. However, the road can just as easily hang from the arch. An arch bridge looks a bit like a bicycle wheel. Is the comparison valid? How do spokes hold you up when they can only carry force in tension?
The main problem with a column is that it can fall over, or can be pushed over by wind or other forces. To prevent columns falling over, we can brace them with guy ropes. This is an old method of loading wool bales using a 1-horsepower winch. The pole is held up with guy ropes. However, as well as falling, a column can buckle. Let's look next at buckling in a column. These guy ropes stop it falling over, but they don't stop it buckling. This column will take 1 brick before it buckles. So add a set of guy ropes to stop the buckling, and it will take 3 bricks. It now buckles in an S-bend. Now we'll stop the S-bending with more guys. It will now take more bricks than we dare load on it. So this is why we see so many guy ropes on a tower. It allows the tower to be built with as little steel as possible. This flare stack is more rigid, so 2 sets of guys are enough. This light pole is stiffened differently, so 1 set is enough. A yacht mast is stiffened in a similar way. A TV tower has guy ropes of steel and no central column.
If you hold out your arm, this is a cantilever. If you have even a small load, you can feel your muscles screaming. The muscles on top are in tension. The ones underneath are loose. We call the force here a bending force. Tension on one side and compression on the other. A cantilever is a type of a lever. In this park in Argentina, the gardener doesn't trust the strength of a Moreton Bay fig tree. Lamps and signs are cantilevers. Because of the leverage, it is very difficult to put much load on the end of the arm. This crane, for example, can take light loads at the end and heavier loads closer in. This crane is a cantilever. It's thicker at the base where most of the leverage is. A tower is similar because when the wind blows, it is a cantilever. Most towers are thicker at the base, and in a wind, they are all cantilevers. Wings are also cantilevers. On the ground, they are bending downwards. However, in flight, it is the reverse. Still cantilevers, but the bending is now upwards. Cantilevers are more stable if 2 are joined together. Or cantilevers can be back to back, such as this swing bridge or this circus performer. This too could be called a cantilever bridge, though it is not at first obvious.
If we lie like this, we can feel the force in our muscles. The stomach muscles are in tension and the back compression. This is bending. We can see these forces in this simple demonstration. If we hold the blocks like this, they have very little stiffness. However, turn them over and the story changes. The elastic band is now taking the tension load. If we tighten the elastic, we have a stiff beam that can take load. The elastic is in tension and the wood at the top is in compression. Bricks can be held together with steel reinforcing. If we tighten the steel before we put the beam in place, it is called pre-stressing. The steel is in tension and the masonry is in compression. We do it this way because brick or concrete are strong in compression and very weak in tension. If we don't tighten the steel, the concrete or bricks will crack and the steel will rust. If the reinforcing is tightened after the structure is built, it is called post-tensioning. So if we tension the steel, the bridge won't crack. Let's test this bridge properly. The bricks have crushed a little on top, where they are in compression, and cracked in tension down the middle. A real bridge would have extra reinforcing steel to make sure this does not happen. All concrete bridges have steel taking the tension load. The cables can run along the bottom, the top, or both. In fact, many cables follow a curved path. This arrangement with the reinforcing on the bottom works well as a beam, but it obviously doesn't work as a cantilever. The reinforcing needs to be on top for a cantilever and on the bottom for a beam. So a bridge normally has the reinforcing cables like this. This is fine when the bridge is finished. However, many bridges nowadays are made by the incremental launch method. They are pushed out from the shore. The concrete sections are cast in moulds on one bank. Reinforcing steel is placed first to stop the concrete cracking, as we saw with the bricks. Tubes are also laid in place in the concrete. They are threaded with wire cable, which provide the tension needed in the bridge. However, if we launch the bridge like this, it will fail. So for the launch, there are extra cables along the top and bottom. They can be removed afterwards. The bridge can be made as a hollow box section or an I-beam shape. When the concrete is set, the section is pushed out onto the piers. Powerful jacks do the job. The launching jacks lift the beams, then push everything forward. To avoid pushing the piers over, workers place Teflon-coated mats under the beams. Even with the extra steel cables, a concrete section would break before it reached the piers, so a steel nose is bolted on.
You can feel the shear force when you rub your hands together, or when you drag something. Shear is a pair of sideways forces. This pile of paper is barely able to hold its own mass. The sheets all slide over each other, allowing the pile to bend easily. This beam is failing in shear. If we fix the sheets so they cannot shear, the beam becomes far stronger. A shear force is sideways. If a material fails this way, we say it has failed in shear. On a bridge, the shear force is large near the piers, but low near the middle. If we take a piece of metal and put two forces on it like this, then the atoms can be forced to slide past each other. The metal has failed in shear. This is the most efficient way of cutting metal. Tin snips and scissors work in this way, which is why they are sometimes called shears.
Here a beam has been reinforced by rods below. The rods are in tension and the beam above is in compression. If we look at this beam, we will see that the steel is mostly on the outside where the maximum force is. They are called I-beams because the cross-section is in the shape of an I. The role of the web is to hold the two sides apart and withstand a small amount of shear force. You can cut holes in the web without weakening the beam. Nowadays, wooden I-beams are replacing solid wood.
This force is called torsion, which means twisting. A spanner applies torsion or torque when it tightens a bolt. Too tight and the bolt will fail in torsion. Here, the producer of this video is about to inadvertently demonstrate how a load-bearing member can fail in torsion. During the abseil, the foot catches, the leg twists. That was the bone failing in torsion. A difficult rescue now lies ahead. The leg bone has a characteristic helical-shaped break. Doctors call it a spiral fracture, which shows they don't know their geometrical shapes. Broken car axles look like this.
When we build a structure, we aim to use as little material as possible. Yet it still has to be strong enough to do the job. Over the years, builders have learned how to make a house out of the minimum amount of material. Take a floor. Badly built, this could happen. Under load, the joists will twist and buckle, very similar to columns. To prevent this, noggins are used. They stop long pieces buckling. House frames always have noggins to make the walls stiffer. Diagonal bracing also makes structures stronger. A triangle is magic, it won't move. By using a series of triangles, it is possible to make a beam called a truss. It is a way of using very little material.
Sections should be as short as possible to prevent buckling. The material in the center contributes nothing to the strength, so structures should be hollow where possible. Even the bracing members can themselves be hollow or made up of smaller members themselves. If you look around you, you will see that when it comes to efficient lightweight structures, nature has been doing it for millions of years.